Sound waves. In sound waves, we've once discussed on the definition, and I also gave you an explanation to show that sound does not travel through vacuums. We differentiate between sounds, noise, and music. I also state the characteristics of sound waves. I differentiated between light and sound waves and also state the differences between sound and radio wave. And lastly, we discuss about echo and its applications. Now students, at the end of today's lesson, you should be able to 1. Define resonance. 2. Give an explanation on the experiment of vibration in strings. 3. Describe a wave in strings and the mode of vibration of stretched strings. And lastly, solve some calculations on the mode of vibration of stretched strings. What is resonance? Resonance occurs when two objects of the same length are placed side by side to each other and one of them vibrates at natural frequency. Or you can refer it as a phenomenon in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude at a specific frequency of operation. From this explanation, you observe that the second object is forced to vibrate with the frequency of the first object. Now, looking at the diagram we have on our screen, it shows 6 pendulums which are A, B, C, D, E, and X. From our observation, X and C are of the same length. So, when X is set into oscillation, after some time, it is observed that all the pendulum will also be set into oscillation with small swinging, with the exception of C. Based on this, we say that C has been set into a resonant vibration by X, or a resonance has occurred since C has the same length as X. Our next line of discussion is the experiment to show the vibration in strings in order to demonstrate the dependency of frequency on length, tension, and mass per unit length of the string. From the image you can see on your screen, we have a sonometer, which is used to study the frequency of notes obtained from the stringed instrument. The sonometer consists of a hollow wooden box S within a thin horizontal wire attached to one end, W. A mass is hung at the side of the sonometer. Then, a wire is passed over a grooved wooden wheel bridge, that is, between B and D, and are placed under the wire so that the wire can be varied by moving one of the bridges. The length of the wire between B and C is read from a fixed horizontal point F, calibrated in millimeter on the box below the wire. It is based on this the following conclusion we reached. 1. Frequency is inversely proportional to length for a given tension and strength, that is, mass per unit length. So mathematically, we have frequency is directly proportional to 1 over length, which is F is proportional to 1 over L for a given tension and strength mass per unit length. 2. Frequency is directly proportional to the square root of tension for a given length and strings, which is your mass per unit length. So, which means we have F is proportional to the square root of T for a given tension and strings, which is mass per unit length. And 3. Frequency is inversely proportional to the square root of the constant M for a given length and tension, that is mass per unit length. There we have F is proportional to the square root of 1 over M for a given length and tension. Our next line of discussion is on waves in strings. In physics, when we made mention of string, what we are referring to is rope. So based on this, we want to look at the waves in strings. When waves travel along horizontal rope, fixed at one end, and the other end is free to move, sound is generated from one fixed string or wire that allows to move at the other end. The type of wave that occur in string is called a transverse wave, and the wavelength is in lambda. So the distance between the consecutive nodes, which is lambda, is given as L. So by so doing, we have L is equal to lambda divided by 2, where lambda is equal to 2L. A good explanation of this is represented in the diagram you can see on your screen, where we have the full length, that is the distance between the first node and the second node, NN, is given as L, and L is now equal to lambda divided by 2. But we have frequency to be equal to velocity divided by wavelength, which is V divided by lambda, which is our wavelength. By substituting the value of frequency into this, which is 2L, then we now have it as V divided by 2L. Since this velocity of the string is now given as the square root of T over M, where F is now given as V divided by 2L. By making V the subject of formula, we now have V to be equal to 2 frequency times length. We now substitute the value of V into the equation and make F the subject of formula. At the end of this, we now have our F to be equal to 1 over 2L square root T over M, where T is equal to tension, L is equal to length, M is equal to the mass per length, and F is equal to frequency. So let's take a look at an example regarding this. A transverse wave is applied to a string whose mass per unit length is 3 times 10 raised to the power of minus 2 kg per meter. If the string is under a tension of 12 Newton, calculate the speed of propagation of wave. From this, the tension, which is the force, is given as 12 Newton, and we now have the mass, which is in kilogram per meter, to be given as 3 times 10 raised to the power of minus 2 kilogram per meter. So by recalling our formula where we have V, which is now equal to the square root of T divided by M. So we substitute the value of our tension and the mass into the equation. So we divide 12 by 3 times 10 raised to the power of minus 2, and we end up having it as square root of 400. And the square root of 400 gives us 20 in meter per seconds. Now students, we've come to the end of today's class. In today's lesson, we have been able to define resonance. We described the experiment of the vibration in strings. We explained the wave in strings and the mode of vibration of stretched strings. And we also solve some calculations on the mode of vibration of stretched strings. The following exercise is meant for you to solve. Kindly solve this and send your solution to the school email. Thank you for watching.